You will understand which companies are racing to build the world's first commercial fusion reactor, what's stopping them, and who's actually closest to winning. For 70 years, fusion power was always 30 years away. Now, at least 5 companies believe they'll have a working commercial reactor within the next decade, and they can't all be right. Google just signed a partnership with a fusion company. Microsoft committed to buying power from a fusion plant by 2028. Helion broke ground on what they're calling the world's first commercial fusion facility. The National Ignition Facility achieved net energy gain in December 2022, proof that fusion ignition is no longer theoretical. Commonwealth Fusion Systems is constructing Spark in Massachusetts. ITER, the 35-nation government project, keeps delaying, now pushed to 2039 for full operation. Private companies smell blood. The question isn't if fusion works anymore. It's who gets there first and what they're not telling you about the engineering nightmare standing between breakthrough and grid connection. You're about to understand the hidden battle for the first commercial fusion power plant, which companies are actually building reactors right now, why the 2022 breakthrough didn't solve the real problem, and the engineering trap that could bankrupt even the best-funded fusion company. December 2022. Lawrence Livermore National Laboratories National Ignition Facility did something unprecedented. They fired 192 laser beams at a tiny fuel pellet containing deuterium and tritium. For a fraction of a second, fusion ignition occurred. The reaction produced more energy than the lasers delivered to the target. This was inertial confinement fusion, compressing fuel so violently that atomic nuclei fuse. Headlines screamed breakthrough. Scientists celebrated achieving net energy gain. But here's what they didn't tell you. That reactor will never power a city. The lasers consumed vastly more energy than the fusion reaction produced when you count the full system. The Q factor, energy output versus input, was positive for the fuel capsule, but deeply negative for the facility, and it can't run continuously. It fires once, then takes hours to reset. It was proof that laser fusion ignition works, not a blueprint for a power plant. The real race is happening elsewhere. Commonwealth Fusion Systems, backed by Bill Gates and now partnered with Google, is building Spark, a compact tokamak reactor using high-temperature superconducting magnets to contain plasma. They're targeting net energy demonstration in 2025 with a commercial reactor called ARC to follow. Helion Energy made an even bolder move. They signed a power purchase agreement with Microsoft, promising to deliver electricity from fusion by 2028. That's not a research goal. That's a binding contract with penalties if they fail. Microsoft's data centers are devouring power. Helion promised to deliver it from fusion. That's how confident they are. Then there's TAE Technologies, pursuing a radically different approach, trying to achieve fusion using hydrogen and boron fuel instead of deuterium-tritium. This tritium-free fusion would avoid one of the industry's biggest headaches, but it requires plasma temperatures nearly 10 times hotter than deuterium-tritium fusion. No one has achieved break-even with this fuel cycle yet. It's a massive technical gamble. Meanwhile, ITER, the International Thermonuclear Experimental Reactor in France, was supposed to be the solution. 35 nations collaborating, tens of billions of dollars invested. The world's largest tokamak reactor design. But ITER keeps slipping. First plasma, now delayed to 2025. Full deuterium-tritium operation, pushed to 2039. It's a government mega-project, drowning in complexity. Private companies looked at those delays and saw opportunity. In Washington state, Helion didn't just make promises. They secured land, broke ground, and started construction on what they claim will be the first commercial fusion power plant. They're using a pulsed, non-tokamak design, compressing plasma with magnetic fields, extracting electricity directly without steam turbines. A fusion energy company is already seeking grid interconnection approval from PJM, the operator managing the power grid for 13 states. That's not vaporware. That's permitting, regulatory compliance, the unglamorous work of actually connecting fusion to the electrical grid. But here's the twist the press releases skip over. Achieving fusion ignition, what NIF did, is not the same as building a reactor that survives continuous commercial operation. Fusion reactors face an engineering nightmare, neutron bombardment. When deuterium and tritium fuse, they release helium and a flood of high-energy neutrons, carrying 80% of the fusion energy. Those neutrons slam into the reactor's first wall, the inner surface facing the plasma, at incredible speeds. Over months and years, neutron bombardment degrades materials, makes metals brittle, creates cracks. The first wall materials challenge is brutal. No material has been proven to withstand decades of fusion neutron damage at commercial scale. The reactor has to be periodically rebuilt. If the first wall fails faster than expected, your economics collapse. Then there's the tritium fuel breeding problem. Deuterium is abundant. You extract it from seawater. But tritium is radioactive, rare, and decays quickly. It doesn't exist in nature in useful quantities. You have to breed it inside the reactor using lithium blankets surrounding the plasma. Neutrons hit lithium, producing tritium. Except breeding tritium at the rate you consume it, achieving tritium self-sufficiency is extremely difficult. If your reactor can't breed enough tritium to sustain itself, you're stuck buying it externally. And there isn't enough tritium on the global market to fuel a commercial fusion industry. It's a closed-loop problem. You need a working reactor to breed tritium, but you need tritium to run the reactor. No tokamak has demonstrated continuous tritium breeding at break-even yet. TAE Technologies is trying to sidestep this entirely by using hydrogen-boron fuel, which produces no neutrons and needs no tritium. If they succeed, they avoid both neutron damage and tritium breeding. But their approach requires plasma temperatures exceeding 1 billion degrees Celsius and has never reached net energy gain. It's high risk, high reward. Meanwhile, the competitive landscape is intensifying. Google's partnership with Commonwealth Fusion isn't charity, it's a strategic bet on tokamak design with high-temperature superconducting magnets. Microsoft's deal with Helion is a bet on pulsed magnetic compression with direct energy conversion. These tech giants are the first customers because their AI data centers need gigawatts of clean power, and the grid can't supply it fast enough. According to industry analysis, private fusion companies raised billions in funding in 2023 and 2024. The top players are distinguished not by who has the best plasma physics, but by who has binding contracts, construction timelines, and grid interconnection plans. But skepticism remains. The Australian Energy Council asked bluntly, are these fusion deals based on reality or a dream? Helion promised power by 2028, less than 4 years away. No fusion reactor has ever operated continuously for months, let alone years at commercial scale. Can they really go from prototype to grid-ready power plant in that window? The engineering leap is staggering. Here's what's at stake. Whoever reaches commercial fusion first doesn't just win a contract, they define the industry standard. If Helion delivers power to Microsoft in 2028 using their pulsed design, every other approach risks obsolescence. If Commonwealth Fusion's Spark tokamak hits net energy first and scales to arc, the tokamak becomes the template everyone copies. The loser doesn't get second place. They get investor exodus, talent drain, and shelved technology. The market is multi-trillion dollars. Energy independence, climate solution, geopolitical power, winner takes all. But if the first commercial fusion plant fails, If it can't run reliably, if the first wall degrades faster than predicted, if tritium breeding falls short, if costs spiral out of control, it poisons the entire industry. Investors lose billions. The jokes about fusion being perpetually 30 years away come roaring back. The reputational damage could set commercial fusion back a generation. Right now, the progress is tangible. Hellion's groundbreaking ceremony happened. Commonwealth Fusion's Spark construction is underway in Massachusetts. Grid interconnection filings are real. Microsoft and Google are betting real capital, not just press releases. But the hardest engineering challenges remain unsolved. Making the reactor last, breeding tritium continuously, handling neutron damage to first-wall materials, running for years without catastrophic failure, achieving a Q factor high enough that energy output vastly exceeds input when you count the entire system, not just the plasma. China's East Tokamak set records for plasma confinement duration, over 100 seconds at high temperature. Japan's JT60SA tokamak, the world's largest operational tokamak, began experiments in 2024. The science is advancing globally, but none of those are commercial power plants. They're experiments studying plasma containment, testing stellarator and tokamak reactor designs, pushing the boundaries of magnetic confinement fusion. The leap from experiment to grid-ready infrastructure is where ITER stumbled. It's where private companies are gambling everything. So who's actually closest to winning? The company with the binding contract and the earliest deadline, Hellion, promising Microsoft fusion power by 2028. They have the most to lose and the most to prove. If they deliver, they rewrite energy history and own the commercial fusion market. If they miss, the skeptics were right, and the fusion dream gets pushed back another decade. Commonwealth Fusion's Spark timeline is slightly more conservative. Net energy demonstration targeted for 2025, commercial reactor later. But their tokamak approach is more proven, their partnerships deeper. TAE's tritium-free approach could leapfrog everyone if the physics works, but it's the longest shot. ITER will eventually operate, but by 2039, the private sector will have already decided the winner. The hidden battle for the first commercial fusion power plant isn't about science anymore. It's about engineering endurance, materials science, tritium breeding, and whether anyone can cross the finish line before their funding or their reactor walls give out. 1. Fusion ignition is solved. The National Ignition Facility proved it in 2022, but the engineering durability problem of neutron bombardment, tritium breeding, and first-wall materials is where the real battle is fought, and no one has solved it at commercial scale yet. 2. The first company to deliver commercial fusion doesn't win a prize. They own the entire market standard, define the technology template, and leave every other approach obsolete. 3. Microsoft and Google aren't betting on science experiments. They're buying survival insurance for their data centers' exploding energy demands, and their contracts have teeth. If fusion companies fail to deliver, there are financial penalties and reputational collapse. If you want more investigations into the technologies reshaping infrastructure before the headlines catch up, subscribe now. Next, we're uncovering why the race for grid-ready fusion is colliding with an even bigger bottleneck: the materials that can survive it. Don't miss it.